All right. All right. So we're going to start with Rydberg equation, all right, which is a energy equation, and so you have E is equal to it's a little light, okay. E is equal to lambda. All right, so you should know all these already. H nu, which is equal to H C over lambda. All right, for the Rydberg constant, you have R sub H, and that is your 1 over N sub F squared minus your 1 over N sub I squared. All right, and so this is transitions of your electrons, and so you have your energy level. All right, so you have the lowest energy state, that is the ground state, N is equal to 1. Then you have a higher energy level, that is N is equal to 2. And then higher, N is equal to 3. And then N is equal to 4. And it will come here to where the energy is 0, where N approaches infinity. All right, and so what we're doing is we're seeing the electrons go from one N energy level to another. All right, and so in this equation, what we're looking at is an electron that is going from, say, an N is equal to 2 to an N is equal to 1 transition. So when the electron goes from a 2 down to the 1, that is the highest energy transition that you can get. And in the region of your electromagnetic spectrum, this is in the UV region. Anytime you're going down to a 1, so whether it's 2 to 1, 3 to 1, 4 to 1, anytime you're going down to the ground state, the energy is ultraviolet. So remember your spectrum. So low energy, you got your radio waves, then you got your microwaves, which are higher in energy. Then you have infrared. Then you have your visible. All right, and that by the red, the color we're going to start with is red, infrared, red, and that is your Roy G. Biv. All right, so when you get the violet, after that you have your ultraviolet, in near and far, but I just put it together as ultraviolet. Then you have your X-rays, and then you have your gamma rays. All right, so when we're doing our electron transitions, we are, when we go down to the N is equal to 1, we're in the ultraviolet, largest energy for electron transitions. When we're going down to 2, we're in the visible. So 3 down to 2, 4 down to 2. When the electrons go down to the N is equal to 2 quantum number, then we are in the visible. And that's how we get our line spectrum of the different elements. And then when we go down to 3, then we're in the infrared region. So we have our Lyman, Balmer, and Paschen series for these transitions. All right, so we can calculate the energy of these transitions by using Rydberg. Right, so if we wanted to calculate the energy when an electron goes from N is equal to 4 to N is equal to 2. All right, and so you have your energy is equal to the Rydberg constant, 1 over N sub F squared minus 1 over N sub I squared. Okay, so Constants, and then look up your Rydberg constant. So the Rydberg constant, R sub h, 1.097 times 10 to the 7th. That is meters to the minus 1. All right, that is not the units that we want. So, okay, so what we're going to find here is 1 over lambda. So when your Rydberg constant is given in meters to the minus 1, which is given in your inorganic book, usually it's given in joules, but here it's given in meters to the minus 1. So we're finding the 1 over the wavelength. And then your n sub f, so the final, we're going down to 2, 1 over 2 squared minus 1 over 4 squared. All right, so you push the buttons on your calculator. That. And that will give you 1 over lambda. 1 over the wavelength is, let's give all the numbers, 2.056.875 meters to the minus 1. All right, so I'm not going to give that as my final answer. I want the wavelength to be my final answer. And so I invert that. And I get to my 4 sig figs that the wavelength is 4.862 times 10 to the minus 7. All right, so that is then in meters. This is meters to the minus 1, and then I inverted it. All right, but if the question in this problem is going to be to find the wavelength, find the frequency, find the energy. All right, and well, if this is actually nu bar, so if it is then nu bar, which is actually what the units are for your IR, if you're running an IR, it's actually centimeters to the minus 1, but that is a wave number. Nu bar is wave number, which is equal to 1 over lambda. All right, so we have our, if we wanted to go next to energy, E is equal to, on your equations, E is equal to h nu, which is equal to hc over lambda. So we have lambda, and then, well, we could also say that that is equal to hc nu bar, so either way you would want to do it, because 1 over lambda is nu bar. All right, so then you put in your constants. So you look up Planck's constant, 6.626 times 10 to the minus 34. Yes, that's what I was expecting for that one. All right, so you have 6.626 times 10 to the minus 34 joules times seconds. And then for the speed of light, c, 2.998 times 10 to the 8th. That's what I was expecting. 2.998 times 10 to the 8th meters per second. Divided by your wavelength, which we calculated as 4.862 times 10 to the minus 7 meters. All right, and so this is an energy. Well, you need to know what a joule is. So a joule is a kilogram meter squared per second squared. So you have to know that. Joules here is not very helpful in the units. So you should change that to kilogram meter squared per second squared. So this second gets rid of one of those seconds. Your So you have time seconds, speed of light. All right, one. All right, so when we do a unit check, E is equal to lambda, E is equal to H nu, HC over lambda. Joules times seconds, meters per second, meters. All right, what the heck is going on? All right. Times frequency, which is 1 over second. So that gives you have C is equal to lambda nu. And so lambda is equal to so E C over lambda. Okay, so now what I'm having a problem with. Yes, so scratch that. You don't need joules because that's your final answer. All right, so you see when you have joules times seconds, so the seconds will cancel here, your meters will cancel here, and of course you have joules. So you just push the buttons and you get your answer. Energy. So you have your 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8th divided by 4.862 times 10 to the minus 7. All right, so you get your energy. And the energy for this equation is 4.086 times 10 to the minus 19 joules. All right. All right, so what I'm going to do is calculate the Rydberg constant. All right, so if you want your E is equal to H nu is equal to your Rydberg constant 1 over n sub f squared minus 1 over n sub I squared. Most of your Rydberg constants that I've seen, except not in this book, puts that in terms of energy. And so now we know the energy. We know that it is 4.086 times 10 to the minus 19. And then we also know that this was 1 over 2 squared minus 1 over 4 squared. And so I'm going to solve for the Rydberg constant in terms of energy. So I'm going to then divide that by. All right, so in most books, you will find the Rydberg constant given as 2.179 times 10 to the minus 18 joules. So that's the way that we did it in Gen Chem. The Rydberg constant was in joules, not in meters to the minus 1. All right, so they are related because meters to the -1 is nu bar, and so your E is equal to HC nu bar. All right, and so they are directly proportional because that a constant times a constant is another constant, and so your energy and your wave number are directly proportional. The higher the wave number, the higher the energy. So this book gives the units for the Rydberg constant in meters to the -1. And so you're not solving for energy, you're solving for 1 over lambda, which is nu bar, and then you would have to convert that into energy. So imagine a lot of books would have it in both joules and in meters to the -1. That's just the difference of your Planck's constant times the speed of light. So if you wanted your Planck's constant in energy and it's given in 1 over the wavelength, you would have to multiply it by Planck's constant in speed of light. Then you would have an energy which is 2.179 times 10 to the -18. The number that they have the That's 2.179 times 10 to the -18. All right, so that is interesting that your Rydberg constant would be given in both meters to the -1 and in joules, I believe. I'm going to give you the Rydberg constant in terms of energy in joules, not in terms of wave number as they have in the back of the book. All right, and so your equation that you would use is E is equal to the Rydberg constant, 1 over n sub f squared minus 1 over n sub I squared, and then you would plug in your Rydberg in energy. So if the Rydberg units are energy, then that's what you're getting, energy in joules. If the Rydberg constant's in meters to the -1, then you're getting 1 over the wavelength, which is the wave number, is equal to the Rydberg constant, 1 over n sub f squared minus 1 over n sub I squared. So you'll see a whole bunch of equations for these conversions, the transitions of electrons, and they may look completely different, sort of like your list of R values. They may look completely different. They are all the same. All right, so there'll be a question where you have the Bohr model of electronics, energy level down to the energy level, energy, the frequency, and wave number. We didn't calculate the frequency, so let's calculate the frequency. All right, so E is equal to h nu. So divide both sides by h, and that will give you your frequency. So we have the energy that we calculated for this, and that was the 4.086 times 10 to the -19 joules. And then we have Planck's constant, 6.626 times 10 to the -34 joules times seconds. This time I'm not going to mess that up. Just the joules cancel. And you have your frequency, and that is always in 1 over seconds. Note that you need to know that 1 over seconds is called hertz. So if you see hertz, you need to know that that is a 1 over second. So 4.086 times 10 to the -19 divided by 6.626 times 10 to the -34. And you have your frequency as 6.17. 6.167. 36 bigs, 6.167. 6.167 times 10 to the 14th. 1 over seconds. That is your frequency. All right, so the question is going to ask, calculate the energy, the wavelength, the frequency. So you will need to be able to do that with that type of question. So I'm not sure which way to do that, but two ways there. I always use that as the one that look, most likely using the one that is minus 1, since that's quantum numbers. All right, so quantum numbers. So you have your N, your L, your M sub L, and your M sub S. N is your principal quantum number. That's your energy level. All right, so that's when N was the same one as above. When you're going down to a lower energy level, you're releasing energy, and that energy released is either in the ultraviolet, infrared, or visible. All right, and so this goes, it starts at 1. So the first thing we have is the 1s, and then 2s, and 3s, and 4s. So it goes from 1, then 2, of course, 3, 4, 5. All right, so that then goes to infinity. We know up to 8. You have an 8. You have an 8. 7. Well, yeah, that's the next. That's 2, or made, not found. All right, so that's your principal quantum number. That is the first number in any of your electron configurations. That is the principal quantum number. Your L, the L values can be 0, 1, 2, 3, 4, 5, but the maximum it can be is n minus 1. So if n is 1, the only number that this can be is 0. If n is 2, well, then it could be 0 or 1. If it's 3, it can be 0, 1, or 2. It can be to a maximum of whatever you had for n minus 1. All right. And so you need to know that your second quantum number tells you your subshell. So if it is 0, you're talking about S. So the 1S is 1, 0. If you have your L to be a 1, that means P. So if you're the 2P, you are 2, 1. And then if you have D, all right, so if you had a 2D, and you know that doesn't exist, because if you had a 2, you could only be 0 or 1. So 2 can only be a 2S or a 2P. 3 can be a 3S, a 3P, or a 3D, because it goes up to an N minus 1. When you're a 4, then you could go S, P, D, or F. All right, and so F is all we have on the periodic table, but after F, we just go in alphabetical order. All right, so then this would be G, H, I, J, K, the whole alphabet. So again, we only know up to F. We have not made any elements in the G subshell, but they're coming up because they are to the 8S. After the 8S comes the 5G. So, all right, and so then that's your second quantum number. Those are your energy level, subshell, and then your M sub L, which is probably confuses the most people. All right, so M sub L, this is going to give you your number of orbitals. All right, and so your if you are S, it is a 0. So it goes from negative L, 0 is always included, to a positive L, and these are integers. All right, so negative. So integers are whatever, negative, in this case, whatever, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. All right, so so for example, if we had let's do a 4D. All right, so if we did a 4D, the first quantum number, n, that's 4. So the first one is very simple. It's whatever number they list. The D is the second quantum number, and so you match it up, knowing your L here. So D is 2. So L is 2. Anytime you're D, your L is 2. All right, so now once you have your L value of 2, then when L is 2, your M sub L can be -2, -1, 0, 1, and 2. And these are your orbitals. All right, and so you can get this a bunch of different ways. All right, so here is, I think, the hardest way to do it. Hopefully you know where the D electrons are on the periodic table. All right, so the D elements are the ones in the middle, and there are 10. So if you know that your S holds 2, your P holds 6, your D holds 10, your F holds 14, and you see a pattern, so you keep going in alphabetical order. G is 18, H is 22, it just keeps going up by 4. All right, so you know that the S has one orbital because we know that one orbital holds 2 electrons, spin up, spin down. The P is going to have 3 orbitals. All right, and so it holds 6 electrons. The D has 5 orbitals. All right, and this is how we number the 5 orbitals in the D subshell. All right, so the easier way, I think, to do it is to know that there are 10 electrons that will fit in the D. Every orbital holds 2, so you have to have 5. And to number the orbitals, every single time you number the orbitals, the orbital in the middle is 0. The orbital in the middle is 0. The orbital in the middle is 0. If there's only one, that's the only number you got. All right, numbers to the left are negative, numbers to the right are positive. All right, so it's just like a number line, -1, -2, 1, and 2. So if you add F, it's -3, -2, -1, 0, 1, 2, 3. All right, so that's how you get your number for your M sub L. And then your M sub S is the easiest. That's the spin quantum number. All right, so if it is spin up, you get a +1/2. If it is spin down, you get a -1/2. All right, so now on the board, I have written a 4, 2, 1, 1/2. All right, so we have a 4, 2, 1, 1/2. All right, so we already did 4, 2. It's right here. So 4, 2 means 4, and 2 means D. So now we know it is a 4D. All right, and so we also know that Ds have 5 orbitals. And we always know the one in the middle is 0, -1, -2, 1, 2. All right, so what we want to do is we want to get to orbital number 1 with a spin up. And so you use the bus seat rule, Hund's rule. You put 1 electron in every orbital before you come back and you pair it. Except once you hit right here, you've hit your other 2 quantum numbers. That is in orbital number 1, and it is going spin up. And so that is a 4D4. So then you got to look at your periodic table and know that S starts at 1, P starts at 2, P starts at 3. So ST is a 3D1. I is a 4D1. 4D4. So that's 1, 3, and O is a 4. So from your periodic table, you know that your element is molybdenum. And so that is MO. If we had a 5, 1, 0, negative 1/2. And we wanted to find the element where the last electron had those 4 quantum numbers. So 5, so you simply write the number, 5. 1, you have to know that your L is 0 up to n minus 1. So here it could have been a 0, a 1, a 2, a 3, or a 4. It is a 1. All right, and so when you have the 1, you know that you're talking about the p subshell. All right, and so then you have a p. So you know that the p subshell holds 6 electrons, and so it's going to have 3 orbitals, and we know that the orbital in the middle is always 0. So negative 1 here, positive 1 here. So we're going to put in electrons until we are in the 0 orbital, and it is going spin down. So you got Hund's rule. You put in unpaired electrons first. So 1 electron in each one would spin up. Then once they're all have 1 electron in it, now we go back to the beginning and we start pairing them up. And so when we get here at 0 and it spin down, 0 and it spin down, then we stop. That's the electron that we're looking at. And it required us to put in 5 electrons into the 5p. And so that is a 5p5. Then we come over to the periodic table. Know that S starts at 1, P starts at 2, S starts at 4. So, boron, 2p, aluminum, 3p, A, 4p, IN, 5p. That is 5p1, 5p2, 5p3. 5p5, you have iodine. So that is the element iodine. Right, so the first P is a P1, P2, P5. P, first row P is in the second. 2P starts at 2, 2, 5, and so the S and the P follow the row number. The F do not. Doesn't show up until row 4, but the first is a the first F doesn't show up until row 6. However, that is a 4F. We know that S starts at 1, P starts at 2, we'll get that right. Then you have to know that D starts at 3. You know it doesn't come in until row 4. First row of D is a first row of F is a 4F. You have to go when they start. All right. And then you just count down and add the numbers until you get to the element that you're looking for. So you have a 1s, you don't have a p until it gets to 2. The first p is a 2p. You don't have a d until you get to 3. And you don't have an f till it's 4. And then the 5g would be the lowest one. So when we do our build-up rule, all right, so you have your 1s, and then you have your 2s, and then your 2p, and then you have your 3s, 3p, 3d. It is nice. 1 has 1 thing to put. 2 has 2 things to put there. 3 has 3, and it just keeps going from there. All right, so 4, you're going to have 4 things. S, P, D, and F. 5 is going to have 5 things. S, P, D, F, and G. But note, there are no known elements that have a 5G electron at this point. 6 has 6. S, P, D, F, G, H. All right, so S starts at 1, P starts at 2, D starts at 3, F starts at 4, G starts at 5, and you just keep going, and you just keep going alphabetical order, and you keep adding 4 electrons to the next subshell. All All right, and then of course, the way you fill it, you fill the 1s, then you fill the 2s, and then the 2p, and the 3s, and then 3d, 4p. Oh boy. Follow the bouncing ball. Wow, much better on the, all right, and then you have that. All right, the only time you should ever use this, what I'm doing here, is when you have something that hasn't been made yet. All right, and so you should never use this until you get to your 7p6. So 7p6, that's the last one that we know, that's element 118. So then you're 8s2. So the problem is, at this point, the periodic table stops, and so you don't know what's coming next by looking at the periodic table. All right, so once you have, if you're doing futuristic element number more than 118, then you would have to know that after the 8s2 comes the 5g18. You can't just look at the periodic table because it is not on the periodic table because it doesn't exist yet. All right, so then that would go to the 9s2. After the 9s2, you're going to have 6g18, and then you would have 7f14, and then you would have 8d10, and then you would have your 9p6, then your 10s2. Okay. All right, so the only time you would, again, need to use this buildup chart is when you would say, what element would a 6H10 be? And then you got to just add up all these numbers, which would be quite the task to add up all of these numbers to get what element number is going to be 6H22, or it could say, what's the electron configuration of element number 200 when we made that, and you'd have to add those all up to get here. Otherwise, you just follow the periodic table. I would not use the periodic table. What's the electron? The 1s2, and then the 2s2, and then the 2s2, and then the 3p6, and then the 4s2, and then you have no p's present for you. And 4p6, and 5s2, now your second is now you're at 4p10, and then you're at 5p. Then you start your 6s2, and then you see that you're going down here, and you're going to go down to f. You have to go back, start to 4. You have to 6s2, you have 14. Then you're back up in the B, 5b10, and then your 6p6, and then your 7s2, and then you're back down to your 5, 14. First path is 4, 5, and 14. Back up to the B's, so you have 10, and you're at your 7, 6, and then it ends after 7p6. That is 118 element. That periodic table's from 1994. That one doesn't go up to 118. In 1994, there were 103 that had symbols. So we come up with 14 in 25 years. So at a rate of one element made every 2 years. Although there is a webinar on making of the elements, and they think that the synthesis of elements is going to really slow down. Their method that they have used in the past is not going to work, so they're coming up with a new method to elements. We'll see if they are able to do that or not. But they are working on making the new elements, and I'm sure there will be some excitement when the first G element is made. All right, so that's quantum numbers and, of course, electron configuration. Go to quantum numbers to the electron. Let's look at iridium, and I want the 4 quantum numbers. 4 quantum numbers. So, I think I'll write the actual number so you don't have to do hunt and find. 77. So it has 77 protons, which means 77 is its atomic number. So now if you know what 77 is, a lot easier. 77. So what you need to see is you have to know that D starts at 3, so it's 3, it's not as in 5D. Then you got to count over. Right? So your SC column has D1, D2, D5, and D6, D7. So you have a D7. All right, again, 3, 4, 5 D7. So once you know that it is 5 D7, now you know if you know the rules for the quantum numbers. First one, very simple. It is the 5. D, remember, 0, 1, 2, 3, 4, S, P, D, F, G, alphabetical order. D is 2. Now you have to know that D has your 5 orbitals. You have to know the bus seat rule, Hund's rule, how you put in the electrons. We're putting in 7 electrons. All right, and you also have to know that the one in the middle is always 0, -1, -2, 1, and 2. So you see when you put in your 7 electrons, it stopped in orbital number -1, and it was a spin down. And so there are the 4 quantum numbers for the last electron put into iridium. All right, so it could be give the full electron configuration. All right, so you go to the first prior noble gas. Right, that's Xe. Then you go to 55, and you see that starting the S2. Go down to the 4F14, and then you go up to the D5D7. All right, so let's see if I can remember what I just said. So Xe, that was then the 6S2, 4F14, and then 5D7. And then you'll make sure that that adds up to the 77. Yep, that is 77. So there is your full electron configuration. Note, if you look up the answer for the electron configuration of iridium, they do not list it that way. That way is fine. The way it always is listed is in order of number. 4F14 it would be first, 5D7 would be next, and then 6S2 would be last. So they will always put it in order of the N quantum number. All right, and then, so this would be a great question for calculating the effective nuclear charge. So, and it would be calculated for the 6S2, calculated for the 5D7, calculated for the 4F14. All right, and what we're going to know before we even do this is that when we take and we said, all right, what is the electron configuration of iridium +1? All right, so we learned this rule in Gen Chem that you always take out the electron out of the highest N quantum number. The best reason to put your electron configuration in number order is because now you're going to remove electrons as you go this way. So you always remove it out of the highest N quantum number. If there was a 6S and a 6P, so there would then be a tie, well, then you would take it out of the highest L quantum number. So you would take it out of the 6P before you take it out of the 6S. All right, and so so when you're calculating this, you will find that your 6S2 electron is going to have a much lower effective nuclear charge. That means it's going to have, you have your 77 protons for iridium, and it might feel a +3 versus the D, which would feel, I don't know, +10 versus the F, which would feel maybe +13. You'd have to do the calculations. But so you should have some ballpark idea of what it would be when you're solving for it, all right? Because you know that you're going to remove your 6s2. And so that is going to be XE 4F14 5D7 6S1. All right, and then if you removed another one, you could actually calculate that, and you would see again that your 6S1 would have a much smaller effective nuclear charge. It would only feel, again, about a +3-ish number versus a +10-ish number and a +13-ish number. And so then once those are gone, then you could say, all right, so then you have iridium +2. It's going to be basically the same numbers. So you're going to take it out of the 6s again. So XE 4F14 5D7. All right, and so a very, very stable state for iridium is iridium +3. And now you're going to take it out of the 5D. If you did this calculation again, this is like a +10, this is a +13. All right, and so it's going to take it out of the lower effective nuclear charge. And so that would be 4F14 5D6. All right, there's always exceptions to the rule that do make sense. We're going to do the predicted values, but there could be a thought question like, what would be possibly better than this electron configuration of 5D6? So when you see that, you could say that your F's are full, and that's great. If you are full, you are very stable. That is not going to change. So full is the best. A full subshell is very stable. The second best is if you have half full. So there's stability if the subshells are half full. All right, that means they don't have to pair with anything. They have their own seat. All right, so they really like to be half full. And so they will do stuff that is not predicted in order to be half full. And that would be the case with iridium +3. So for iridium +3, I would not be surprised if you had, all right, so we have the F is full. I'm not going to put it. So you have your 5D, and you have your 6S. All right, and so we have if we go back to the neutral one, you got your 7 electrons in here. And then you had your 2 electrons in here. All right, and so we took out the first one for a +1. We took out the second one for a +2. All right, and then we take out a third one for the +3. So what would not surprise me, there's still one in here. Okay, what would not surprise me here is if this one that is paired up said, well, I would rather go up here and be unpaired. So that would not surprise me. I don't know that this is what happens, but it would not surprise me at all if the electron configuration of iridium +3 would be a 5D5 and a 6S1, where both of these are half full. So whether that is going to happen or not, that depends on what you find when you do the different experiments. But what you would predict is this, and what you would be looking for is, or is it this, which we would also expect to be very stable. Is it more stable than this? You would have to run experiments to see if you had your cation, if it was paramagnetic that had 6 unpaired electrons, or is it paramagnetic that has 4 unpaired electrons? So you'd have to design an experiment to calculate that. But anyway, you should know that a lot of your exceptions are all based on full is very stable. Half full is also very stable. Most of the exceptions are based on that. So the ones that we had to know for Gen Chem, so I will continue to make you aware of those. So you need to know. Chromium, molybdenum, and then your copper, silver, and gold. There's a bunch more, so, but these are the classics. So, all right, so if you did your chromium, chromium is number 24. So you go to the first prior level gas, that's 18, so you got argon, that's 2, starts at 3, 4. You got your argon, and then it is a 4s2, 3d4. Molybdenum is going to be a 5s2, 4d4. All right, so the rules for the columns are going to be exactly the same. So here, which was the reason why I could expect that the possibility of iridium plus 3 being this, all right, so the reason why I would not be surprised to find that is because of what I find right here in chromium. All right, so in chromium, you've got your pair electrons here, and then you have your 4 electrons here. So this electron sees an empty seat back here and would rather be there than paired up over here. Again, that's not something that you would predict, something that, well, this is something that you could say is a high possibility. Then you go and you do your experiments, and for chromium and molybdenum, that came to be true. For tungsten, right underneath it, it was not true. So, you know, again, you have to investigate it. This is a strong possibility. Does that happen or does it not? For chromium, molybdenum, yes, that happens. For tungsten, it does not happen. All right, and so I'm not saying that iridium plus 3 is going to happen. I'm just going to say I would definitely look into that because it is a strong possibility. And so everything here is half full. And so instead of a partially full and a full, everything half full is more stable. Except for when you go down to tungsten, then it is happy being paired over here and having the 4. All right. The column with copper, it's unanimous. All right. So copper is argon, 4s2, 3d9. Okay. So again, chromium is not this. So we know by experiment it is a 4s1, 3d5. All right, so that's the exception. So if I want the electron configuration of chromium, it is not 4s2, 3d4. It is 4s1, 3d5 because that electron is more stable here. And that was done by experimentation. That is a fact that it is more stable when it's 4s1, 3d5. All right, so it's unanimous in this column that instead of having a full S, it is much more stable to have a full D. And so your 4S and then your 3D. All right, so this one was full and this one was one short of being full. So it's more stable to have a full D than it is to have a full S. And so this electron will go here. There's definitely stability in having a full D subshell. It is an obvious stability factor because it happened to all 3 in that column. All right, and so that is not the electron configuration of copper. Copper's electron configuration is 4s1, 3d10. All right, and so your silver is going to be 5s1, 4d10. Your gold is going to be 6s1, 5d10. All right, so there's going to be more to that, but anyway, it's going to be an S1D10 for all of them. The next one down is going to be a 5S1 and 4D10. The next one down is going to be a 6S1 and a 5D10. All right, so those are the only 5 exceptions to what you would predict that you will need to know. And interesting that copper, we know copper comes in two oxidations. All right, so you can have copper plus 1. You can also have copper plus 2. What's interesting is that is not true for silver. The only oxidation that is stable for silver is a silver plus 1. All right, so you will not see silver in any other oxidation. All right, but copper only has 2. Remember, the lower is the us, the higher is the ic. So this is cuprous, this is cupric. The other ones that we will need to know are the iron, which is plus 2, and the iron, which is plus 3. You got your ferrous, you got your ferric. If you're naming it, you can simply call it iron 2 and iron 3. But if I'm putting the name on the test, I'm going to call it ferrous and ferric. You need to know that that's a plus 2 and a plus 3. Tin, SN plus 2, and SN plus 4. All right, the ic and the us doesn't mean a certain number. It doesn't mean they differ by 1. It just means there are 2 stable oxidation states. The one that ends in us is the lower of the 2. The one that ends in ic is the higher of the 2. So this is stannous and this is stannic. If you're naming it, you can name it iron 2 and iron 3. But iron only comes in the 2 stable oxidations of 2 and 4. There's a bunch of others. I don't think others that you will need to know the oxidations for. There's only one stable oxidation for cadmium. It's plus 2. Platinum is always plus 2. Did I give any others? Zinc, it is plus 2. All right, so you'll see that a plus 2 is a very common oxidation state. The only one that I listed up here that did not have a plus 2 oxidation state was silver. All right, and the reason for that is you have an S2 all the time for all of those things. So if you do the electron configuration, there is an S2. Both of those electrons have a very low effective nuclear charge. And so it is easy to remove both of those S electrons. And so you have a lot of very stable plus 2s. Now note that silver does not, although your copper does. But you could predict the reason why silver is only plus 1, because it is an exception to the buildup rule. It doesn't have an S2. It only has an S1 in its electron configuration. So this one is very easily removed. I'm circling the wrong one. This is silver, which is this one. This one is copper. All right, so, but again, copper, it does too. It is able to remove one of the electrons from the 3d10, but the silver is not able to release one of the electrons from the 4d10. All right, and so that again is something that you would suspect. Again, you would then have to investigate it. Copper is able to lose it, but silver is not able to lose it. And so silver only comes as plus 1. It loses the 5s1, and it does not want to give up any other electron. Can you make it? Yes, you can make it. Are they common? No. You can pretty much make anything in a lab. You hit it with enough energy, you can get it to do all kinds of crazy stuff. But in compounds, normal compounds, you will not see silver in any other oxidation state other than a plus 1 oxidation state. And gold, I think, has other oxidations. Don't do many reactions with gold, but I know plus 1 is a very stable oxidation for gold. I think it also has other oxidation numbers. All right, so normal in your transition elements, multiple oxidation numbers. Which is very common. Molybdenum has all kinds of them. Chromium has a bunch of them. So the only ones that are the us and the ic are the ones that have 2 and only 2. The ones that only have 1 oxidation number, there's no us and the ic. There's no zinc us and zinc ic. It's only zinc because it's plus 2. But you will have plumbus and plumbic. That's not one that I have you memorize, but lead is plus 2 and lead is plus 4. say, so plumbous, plumbic. And then the classic is mercury. Because this is a classic ion. There may be others. This is the most common one. This is the only one that is used very often. It is the only, I wouldn't say only, it's the only one that I've ever seen, diatomic ion. So note that Hg2 plus 2, this is of course Hg plus 1, except Hg plus 1 doesn't exist. Sort of like if you wanted hydrogen and you said H, again, you can make that exist, but that takes a lot of work. You can probably make this exist, but that is not how it occurs in nature. So hydrogen is hydrogen gas, H2. That's the way you're going to find it every time. Mercury plus 1, which is the name of it. Mercury 1 is the name, but it doesn't come Hg plus 1. It comes Hg2 plus 2. So each one is plus 1, so it is a mercury oxidation number of 1, but you don't write it as Hg plus 1, you write it as Hg2 plus 2. So if you've noticed, and it looks weird, all right, that you have mercury chloride, mercurous chloride, is Hg2Cl2. And you have to be wondering, why in the heck isn't it HgCl? All right, this does not exist because that is mercury 1. Mercury 1 does not exist as Hg plus 1. It exists as Hg2 plus 2. And so this stays together. In order for this plus 2 to be neutral, you have to have 2 chlorines. All right, and so your Hg2Cl2 is here. Very similar to hydrogen peroxide, H2O2. It is not HO. Is the oxidation of this minus 1? Yes. Is the oxidation of this plus 1? Yes. Does O minus 1 exist? No, it does not. Your peroxide is an O2 minus 2. So anytime you have a peroxide, it has to have an O2 minus 2. O minus 1 does not exist. The oxidation of minus 1 does exist as a diatomic ion. So I said I didn't know any other diatomic ions. Okay, maybe cations I meant. There is a diatomic ion. That is the peroxide ion. All right, and so if you say the empirical formula is here. Right, that is the empirical formula. It's in a 1-to-1 ratio. But the molecular formula is H2O2. And a lot of these oxidations are predicted by doing your effective nuclear charge, see how many electrons are going to be released and what the electron configuration is for that. Not all of them, but many of them can be predicted that way. And others are just experimentation. This is what you get every time, and that's what's in the book. All right. Ionization energy versus electron affinity. If you're doing ionization energy, you need to know that you are making cations. When you're doing electron affinity, you are making anions. All right. For the electron affinity, we only make -1. For ionization energies, we'll have ionization energy 1, which is a +1. We will have an ionization energy 2, which is making a +2. We'll have ionization energy 3, which is making a +3. All right, so let's do, we'll do aluminum. All right, so if we do aluminum, so we're making a cation. All right, and so your aluminum is going to aluminum +1, all right, +1 electron. So you're kicking out an electron. All right, so if we do the electron configuration for aluminum, you got 1s2, 2s2, 2p6, 3s2, 3p1. Neon, 3s2. You have your neon. 3s2, 3p1. All right, so when you take the electron out, it's going to take it out of the 3p1. So here is neon, 3s2. You kicked out an electron. So this is ionization energy 1. All right, I'm going to make up a number, 500 kilojoules. All right. So again, I'm just making up numbers. It is a trend, not a number that I'm looking for. All right, so then the second one, you're going to take aluminum plus, and you're going to go to aluminum plus 2. All right, so this is ionization energy number 2. All right, so now you have your neon 3s2, and now you're going to neon 3s1. All right, and so your ionization energy here is 1,000. Again, just making up numbers. All right, and so then we're going to do aluminum plus 2, going to aluminum plus 3, plus 1 electron. This is ionization energy 3, and this one is 10,000 kilojoules. Again, just making up numbers. All right, 10,000, that's wrong. Not 10,000, 2,000. All right, so this is a neon 3s1, and now this is neon. All right, and so then we're going to go from aluminum plus 3 going to aluminum plus 4 plus 1 electron, and the ionization energy 4 is 20,000 kilojoules. All right, then we're going to do one more. We're going to take aluminum plus 4. It's going to go to aluminum plus 5 plus 1 electron. And your ionization energy 5 is equal to 40,000 kilojoules. All right, so again, I'm making up the numbers, but this is going to be not the numbers you're going to see, but it is. It's all about the amount that it increases. All right, so when you go from ionization energy 1 to ionization energy 2, it doubles. So it does. Here it's a perfect 2. I'm just making up the numbers. So a normal situation is you're going to get about 2 times the ionization energy from a first one to a second one. That is a normal increase in your ionization energy. All right, so then we get another normal increase, a factor of 2, in our ionization energies. Then we don't get a normal increase in our ionization energies. This went up by a factor of 10. All right, from 2,000 to 20,000, it went up by a factor of 10. So this is called a big jump in ionization energy. So it's about the factor that it went up by. It went up by a factor of 10. All right. And now when we go here, you think 40,000, that's more than anything else. Why isn't that the big jump? Well, that again is only going up by a factor of 2. So it's about the factors that it's going up by, not the actual numbers. All right. So when you go from 1 to 2, a normal type jump is about a factor of 2. And so the reason why you get a large factor between ionization energy 3 and 4 is because here is your electron configuration of the noble gas neon. It wants to stay as the electron configuration of the noble gas neon. It does not want to go down to a helium and then a 2s2 and a 2p5. So we went down in energy level. All right, so we took electrons out of the 3p, out of the 3s, out of the 3s. Now we took electrons out of the 2p, and that is going to give you a much bigger jump in energy. And then the next one, you're taking it out of the 2p again, so it is just going to double. All right, so when you have your electron configuration of a noble gas, that is also your stable oxidation. So you look at aluminum, and it is in the +3 column. All right, so most of your compounds that have aluminum, they are going to have aluminum in the +3 oxidation. All of them will have electron state rate of the iron. Hydrogen bonding is very simple. It increases your boiling point, and all you're looking for is OH, NH, or the molecule HF. So an infinite number, because R can be just about, you can come up with an R, I'll come up with another one. We can go on forever. And this one has 2 R's. Note that if you have a nitrogen, and of course if it's tertiary, if all 3 of these are R's, then there's no hydrogen bonding. And of course, if you put an R on the other side, this is not an alcohol anymore, that is an ether, and you do not have hydrogen bonding. So you must have an OH, and there's an infinite number of those, or an NH, and again, there's an infinite number of those, and here, HF, which is 1 molecule. So you can have an infinite number of compounds that have an OH, you have an infinite number of compounds that have NH, and HF is just the 1 molecule that has the hydrogen bonding. All right, and so if you have hydrogen bonding, it's going to increase your boiling point. They're going to stick together. It takes a lot of energy to break apart all those hydrogen bonds and then to finally boil it. And OH is a much stronger than an NH. So if you had similar alcohol to an amine, the alcohol will boil at a much higher temperature than your similar molar mass of your amine. So the OH is stronger than NH. OH, stronger than NH. And HF, we don't really worry about because it's only the 1 molecule. Right. Diamagnetic versus paramagnetic, we covered that a little bit. Again, if you have 1 or more unpaired electron, then you are paramagnetic. If you have all electrons paired, then you are diamagnetic. All right, paramagnetic is, if you're guessing, guess paramagnetic because 90% of the elements but it's pretty high, are paramagnetic versus diamagnetic. Right, so you have the bus seat rule, Hund's rule. You have to put in 1 electron up and then 1 electron down. There's not that many that are all electrons paired. Most of them are going to be paramagnetic. Diatomic molecules. I feel like I wrote this already, but it is this thing. Did I write this already? I feel like I wrote this already. All right, so when you're doing your diatomic so this is only for diatomics. You're going to have your whatever. If you had oxygen atom on this side and oxygen atom on this side, and then they go to make your O2 molecule, you put in your electrons, and you will determine if it is diamagnetic or paramagnetic. You have 1 or more unpaired electrons. All right, so resonance, it is simply, you should be good at this now. NO3 minus would be a good example of something that has resonance. So you would have to draw the structure of NO3 minus. All right, now NO3 minus, nitrogen and oxygen can never have more than an octet. So the most bonds that you can put on this nitrogen is 4. All right, so when you put your 4 bonds on the nitrogen, your nitrogen is going to have a plus charge. 2 of the oxygens are going to be minus. That gives you an overall of a minus charge. And so resonance is simply that double bond doesn't have to go to that oxygen. It can go to this one, or it can go to that one. And so you have 3 resonance structures where the double bond could be here, or the double bond could be down. All right, so make sure you can, and then the arrows for resonance look like that. So make sure that you can do the resonance structures for your different ions are the most common. So your NO3 minus, your NO2 minus, your CO3 minus 2. You'll have resonance structures. All right, so work on the homework and bring in questions on Tuesday. I'm just going to review for the test on Tuesday, which will be over all the topics listed. That you look on Moodle and see all the different topics. If you want another example of any of those topics, ask me Tuesday. We will work all the different topics that you want to work. Organometallic nomenclature will be on the test. Review for that on Tuesday. That was on your lab that you guys turned in. All right.